Hello. In this video, um, we're going to be talking about, what are we going to be talking about? 2.1. Notice that we've already covered 2.2, but I think 2.1 is better after 2.2 once you've kind of seen what a limit is. So 2.1 is supposed to serve as motivation for 2.2, but I think unless you've had some physics, it might be kind of hard to understand. So let's take a look now at going back to 2.1 and take a look at a little bit of motivation. Motivation for limits. And there's two problems that we want to look at. Two problems we want to see. That is a problem of velocity and a problem of the tangent line. Okay, so let's start with velocity. What is velocity? Velocity is the rate of change of displacement or position. Probably better to say displacement, but you could think of it as position over time. What do I mean by that? Well, we're used to thinking about velocity of like vehicles. So, for example, we measure the velocity of a car in kilometers per hour or miles per hour. Okay, so that's the displacement, the number of miles per unit time. And so that would be our velocity. Okay, so if, just to be more specific, if s of t is the displacement function, so s of t is telling you where you are at time t, then we can write the average velocity. The average velocity is the change in displacement divided by change in time. And so this is where we get our units, right? Like miles per hour or kilometers per hour or meters per second. So in this case, yeah, we're looking at change in displacement per change in time. And so we can abbreviate that. If s of t is our function, we might call this the change in s over the change in t. Okay, so if time goes from t equals a to t equals b, can we write this as a formula? Then the average velocity is equal to the displacement at time b minus the displacement at time a divided by b minus a. Good. And again, this is in units of displacement over units of time. And in fact, let's even be more specific. So example, suppose our position function, displacement function, is 4.9 t squared. And we'll say our start time is t equals 5. Then what is the average velocity in the interval t runs from 5 to 6? Well, it's our change in position, s of 6 minus s of 5 divided by 6 minus 5. Right, so that would be 4.9 times 6 squared minus 4.9 times 5 squared divided by 6 minus 5. Good. So if we go ahead and compute what that value is as a number, I believe that is 53.9. Okay, now what's interesting is we can ask, well, what happens as the change in time gets very, very, very small? Is it possible to still be able to compute a velocity? So just like we did in section 2.2, that's why I'm kind of looking at 2.1 later. Suppose that I chop my interval into a smaller piece, so I'm just going from 5 to 5.5, right? Or let's just keep with the notation in the books, 5.1. We'll go ahead and drop it to 5.1. So now the interval is from 5 to 5.1. So we have s of 5.1 minus s of 5 divided by 5.1 minus 5. So we have 1/10 in the denominator. And then we have whatever, 4.9 times 5.1 squared minus 5 squared if you pull out the 4.9, right? But we're just going to go ahead and compute that as 49.49 on your calculator. Okay, and so similarly, you can just keep doing that. Suppose my interval becomes 5.01. Okay, then it turns out that the change in the average velocity becomes 49.049. And what happens if we decrease it even further? The average velocity becomes 49.0049. And so now we can ask, as delta t goes to 0, does delta s over delta t go to a number? And it sure looks that way. In this case, it looks like as t goes to 0, the change in velocity, the average velocity, goes to 49. That's what we're going to predict based on these numbers. And so this 49 right here is what's going to be called instantaneous velocity. Instantaneous velocity. Good. And so this is an important idea, because even though velocity means that you have had to have some kind of change in time, it is possible to think of velocity as an instantaneous measure if you think about it in this way. So the instantaneous velocity is the value that you get from your average velocity as the change in time goes to 0. Okay, so that's a really important, and actually it was a very groundbreaking idea at the time. So that's the instantaneous velocity. You'll have some example solutions or example tables to look at in the homework from 2.1. Okay, I just wanted to mention now that we were looking at s of t equals 4.9 t squared at t equals 5, right? And we were looking at the average velocity. Is there a graphical interpretation of average velocity? Here's my 4.9 t squared, and we're sitting here at t equals 5. This is not to scale, right? Let me pause that for a sec. Okay, so I was just double checking my computation here. This is 4.9 times 25 is 122.5. So that's why I'm saying this is not to scale, but we want to be able to see what we're doing here. And so over here, we'll say that this is times 6, right? This is where we started. And so this is, in fact, what I could say, instead of computing the numbers, I could say this is s of 6. And so what is the slope of this line right here? The slope of this line is s of 6 minus s of 5 divided by 6 minus 5. Does this quantity look familiar? This is the average velocity. Okay, so then what we did was we went to 5.1, right? Again, this is not to scale. It would be too close for me to see. And then we computed this velocity. Oops, that's kind of bending. Sorry about that. But this is the slope is s of 5.1 minus s of 5 divided by 5.1 minus 5. And so what we were doing then is we can think of our x's as decreasing to 5, and we're computing the slope between the 2 points. So we're computing the slope between 5 s of 5 and we could just say x f of x as x approaches 5 from the right. Okay, and so what we found previously is we found on the last page, we found the slope goes to 49. And so what we can conclude then graphically is we end up with this line right here that only goes through one point of the curve, and that has a slope of 49. Okay, of course that's very steep, so that's not going to be to scale. Okay, so this is called the tangent line. The tangent line. And these lines up here are called secant lines, just to get a little bit of vocabulary. So a secant line is a line that goes through a curve in 2 points, and the tangent line is a special curve that goes through the curve at 1 point. So notice that for a tangent line, if we were just to approach the problem and say, here's a curve, here's a point, this visually may look like the tangent line, but how can I get the slope of that line? Because I only have 1 point. This gets away from that problem, right? Because what you're going to be doing is take the limit of these slopes, and we'll be able to compute that. Okay, so this is the tangent line problem. The tangent line problem being, again, we want the slope of a line, but we only have 1 point. Okay, so the limit is the answer, and we will get much more in depth in this later on. This section 2.1 is simply for motivation for 2.2, but we reverse the two things. So okay, so I only assigned a couple of problems from 2.1, and they're mainly just compute some numbers on your calculator. All right, I will see you later.